Hello everyone and welcome back once again to this lecture series on aluminum based alloys and metal matrix composites. Alright, so we have been talking about grain refinement right now. This is one more mechanism that we have for strengthening aluminum alloys. And in the previous class, we have discussed the Hall-Petch relationship with regard to grain refinement strengthening. Right, so as the grain size D decreases, strength increases. This is due to the fact that as you decrease the grain size, you basically increase the grain boundary area per unit volume, and since the grain boundaries act as hindrance to dislocation motion, the strength will increase as the number of grain boundaries increases. Okay, and we have actually derived this Hall-Petch relationship based upon a theory which was proposed by Cottrell and then later extended by SLB, Frank and Navarro. So this theory is based upon the piling up of dislocations at grain boundaries. So if you consider any pile up of a given length, inside a grain like this, where the grain boundaries stop the dislocations as they encounter the boundary. From this, you can actually derive this Hall-Petch relationship based upon the stress which is developed at the tip of the pile-up. Okay, so that's what we did in the previous class based upon that stress tau s and a critical stress which is needed for the dislocations to move over to the next grain tau c. We actually derived this Hall-Petch relationship. Okay, but there are certain limitations of this pile-up theory, because as we have seen, this is based upon the stress which is developed by the dislocation pile-up. So you need a large enough pile-up for that to occur. But if the grain size is very small, then the pile-up will also be small, and therefore you cannot really consider the approach that we had taken to arrive at the Hall-Petch equation. Okay, in that case you need to consider other equations also, right, when the grain size becomes very small, right, because for a small grain size the pile-up will also be smaller. And the other problem is, here we have talked about grain boundaries as obstacle to dislocation motion, but grain boundaries can also act as dislocation source. right? So the grain boundaries are not only sink for dislocations, but they can also be sources for dislocation, right? So that is something which is not considered in the pile of theory. It only considers grain boundaries as the obstacle or sink, right? And the other issues with this model or this theory is the fact that for the pile up to occur, the dislocations movement also have to be limited or restricted, right? And we have seen that the stacking fault energy will play a role in that. If the stacking fault energy is low, then you can expect the dislocations movement to be restricted. But for high stacking fault energy materials, the dislocation movement is much greater because of the cross slip. But in both kind of materials, that means low stacking fault energy as well as high stacking fault energy, the Hall-Petch relation is valid, right? So this theory cannot really explain the effect of stacking fault energy, right? And as I said, on the other hand, you also have grain boundaries acting as dislocation source also, right? So considering this, the theories which were later proposed did not really focus on the stress which is developed by dislocation pile up. Rather, those theories consider the dislocation density and the effect of grain size on the same. One such theory or model was proposed by Lee. So this basically considers grain boundaries as sources of dislocations, and therefore the dislocation density would depend on the grain size. And we have also seen before that the strength and dislocation density are related by this particular equation, where rho is the dislocation density and alpha is a constant, typically having a value in the range of zero 0.3 to 0.6. Other terms we have already defined before. G is the shear modulus and B is the Burgers vector. Okay. So now this theory considers the grains as cubic in shape. So let's say we have a grain like this with a particular size, which is defined by the sides of this cube. So let's say that is D, that's the size of the grain. So as I said before, the dislocations will be generated by the grain boundaries, and every grain will have, or every boundary will have their own efficiency of emitting dislocations. So let's say M is the efficiency of grain boundaries to emit dislocations. And this is nothing but equal to the length of dislocation emitted per unit area of grain boundary at yielding. That means when the material has started deforming plastically, at that point, the length of dislocations emitted per unit area of the grain boundary can be taken as M, okay, or the efficiency of the grain boundaries to emit dislocations. Now, the total surface area of a grain like this will be 6d square. And therefore, the total length of dislocation emitted by a grain will be equal to this, right? Because M is the efficiency, so you have to bring M over here. And the factor half comes because each of the faces of this grain is shared by two grains, right? Each face will be shared by two grains, and that is why this factor half comes over here, okay? And the dislocation density is nothing but the total dislocation length divided by the volume. So it is dislocation length per unit volume, that is the dislocation density, right? So therefore we can write dislocation density rho as this one, that is 3d square m divided by the volume of the grain, that is d cube, and this will give you 3m by d as the dislocation density, okay? Now you replace this rho over here in this particular equation, then you will get to the Hall-Petch relationship. Right, so if we consider this term as a constant k, then this will come down to the Hall-Petch relationship. Right? So this is how this particular model or theory, which is known as the grain boundary source theory, will lead to the Hall-Petch relationship. A similar theory, which is based upon the dislocation density, was proposed by Conrad. The theory goes by the name work hardening theory. So this theory says that the distance traveled by the dislocations in the grains is proportional to the size of the grain. So let's say x is the average distance traveled by the dislocations in a grain. Then we can write x equal to beta d, where beta is a constant, right? So we can write x as equal to this, x as equal to beta d, where d is the grain size, and the strain will be given by this. Epsilon is the strain and rho is the dislocation density. So if you replace x over here, you would get this. In terms of the grain size d, okay? So from here we can write rho in terms of the strain and the grain size as epsilon by b beta into 1 by d. So now if you replace this into this particular equation, if you replace rho over here, then it will give you this expression. And now if you take this as k, then this will come down to the Hall-Petch relationship. right? And from here you can also see that the dislocation density increases proportionally with the strain, and this is quite obvious as we have discussed while discussing about the work hardening or the cold working. As you deform the material and provide more and more strain, the dislocation density would increase, and as a result of that the strength will also increase. Okay, so that fact can be also seen from this theory, which again goes by the dislocation density with regard to the strength of a material and the grain size. Okay, right? So these are the different theories which explain the mechanism of grain refinement strengthening, and all of these are based upon the fact that the grain boundaries will either act as obstacles to dislocation motion or they will influence the dislocation density as the grain size is changed. Okay, so let us quickly summarize these grain boundary strengthening theories. We have basically discussed three theories, all of which lead to the Hall-Petch relationship. The first one was grain boundary pile-up theory, which says that the dislocations pile up at the grain boundaries and unless and until a critical stress is reached, the dislocations cannot cross over to the next grain. So you need to provide more energy or apply more load for the dislocations to move, and therefore the strength will increase. Okay. Then we talked about other two theories, which basically talks about the dislocation density rather than the piling up of dislocations at grain boundaries. Because there are some limitations of the pile-up theory as we discussed. So these two theories which are proposed to explain the grain boundary strengthening focus more on the dislocation density and the effect of the grain size on the dislocation density rather than the piling up of the dislocations at grain boundaries. Okay. So there are two theories on this category. One is the grain boundary source theory, which considers the grain boundaries as sources of dislocations. Therefore, as you strain the material, the dislocation density in the grains will depend on the grain size. Similarly, this theory also considers the dislocation density and the effect of the grain size on the same. This is the work hardening theory. So both of these are based upon this fundamental equation which relates the strength to the dislocation density. Right? All right, so this will bring us to the end of these strengthening mechanisms, especially the theories and the different mechanisms that we have for this particular mechanism here, the grain boundary or the grain refinement strengthening. So from now on, we are going to talk about the methods of grain refinement as to how you refine the grain size of a particular material. So this will be our next topic of discussion. But before that, let me also tell you few more effects of grain refinement. For example, if you talk about the fracture stress, this also kind of follows the Hall-Petch relationship. So this stress that you had seen before, that was primarily the yield stress, right? When we discussed the Hall-Petch relationship, the fracture stress will also follow the Hall-Petch kind of relationship with regard to the grain size. So as you decrease the grain size, the fracture stress would also increase. And grain refinement not only increases the strength, but it also improves the toughness. In fact, this is the only strengthening mechanism through which you can increase both the strength and the toughness. For most of the other methods of strengthening, the strength will increase, but generally the ductility goes down, right? But grain refinement is one method which not only increases the strength but also improves the toughness of the material. Okay, but one property that will suffer due to grain refinement is creep, which is a time dependent high temperature deformation process, right? So one of the mechanisms of creep is through grain boundary sliding. So it is not difficult to understand if the grain boundary area increases, the grain boundary sliding will also increase, and that will lead to more creep, and as a result of that, the creep resistance will come down as you refine the grain size. So a fine grained material is never desirable for creep resistance. If you want to use the material at high temperature where creep can occur, it is always recommended to go for coarse grain materials. In fact, it will be best if you can have a single grain material or a single crystal, okay, when it comes to creep. And grain refinement also improves the surface finish after anodizing treatment for aluminum and its alloys. So these are some of the other effects of grain refinement apart from the strengthening. And with that, we come to the end of this lecture. Thank you for your attention.